In this video, we're going to take a look at one of the most important separable differential equations, the one that models exponential growth and decay. This equation has the form dy dt equals ky. So in this expression, dy dt equals ky, the k is usually a real number constant. And so we have a very simple expression for the derivative. The dy dt, or the rate of change of r with respect to t, is equal to k times y. So in the language of calculus, this equation says the rate at which y changes with respect to t, that's the derivative, is proportional to y. So this means that when y is large, then ky is large, so dy dt will be large, and when the derivative is large, the function changes rapidly. On the other hand, when y is small, then ky will be small and the derivative will be small, so y will be changing more slowly. In situations where y models a physical phenomena, y is usually positive. And in that case, we can say a little more. In particular, if k is bigger than 0 in this case, then dy dt equals ky is positive, so y is increasing. And if k is less than 0, then dy dt will be negative because ky will be negative, and then y will be a decreasing function. Many real-life situations are modeled by this equation. Here's a few examples. If P is the population of a group of organisms in time t, say measured in years, and the population grows at a rate of, say, 4% per year, then we model that with the differential equation, dy dt equals 0.04 P. So this says the rate of change of P, dp dt, is 4% of P. That rate of change is in organisms per year because P is a number of organisms and T is in years. So another example, suppose you have money invested in an annual interest rate of 3.5%, and suppose M of T is the amount of money you have at time T in years. Well, how does your money grow? Well, then the rate of change of your money, dm dt, in say dollars per year, is 0.035 M. What this illustrates down here is the fact that when you have lots of money and get some interest, you'll get a lot of interest. If you only have a little bit of money and get interest, you'll get a little bit of interest. So with a lot of money, dm dt is big, your fortune's growing faster. With a little bit of money, dm dt is small, and your fortune is growing slower. We're going to do an example in a moment involving a sample of radioactive material. But through radioactive decay, suppose a material loses, say, 10% of the material present each hour. And let A of t be the number of grams of the material left at time t hours. Well, then we have the expression here. The rate of change of the amount of material, dA dt, is minus 0.1 A. So this means that when A is large, A is decreasing very quickly. That means a lot of material is decaying, putting off radiation. And so when you're in the presence of a large amount of radioactive material, that can be dangerous because that radiation is kicked off as the material decays. On the other hand, if A is small, then minus 0.01 A is small, and the amount is decreasing very slowly, less radiation. Perhaps it's less dangerous to be around a small amount of that material. So let's do an example of this. The iodine isotope I-131 has a half-life of 8.07 days. I'll explain what that means in just a moment. Suppose you produce 0.1 grams of this substance in a lab, and say we're going to take this time of production at time 0. How much will be left after 2 days? Now, I'll find it'll take a little time before we can answer this equation because we're going to have to model the equation that describes the amount of iodine and then do some algebraic work to fill out that equation. So let's let A of t be the amount of iodine left after t days. And because the radioactive material decays at a rate proportional to the amount present, we know there's a constant k such that dA dt equals k times A. So here is that separable equation we've been talking about showing up in this case. We'll have to determine K, but we'll find the information on half-life helps us do that. We do know that K is less than 0 because A of T decreases as time passes. So when a radioactive material decays, the amount present lessens or decreases. So we have dA dt negative. And we know we start with 0.01 grams at time 0, so A of 0 equals 0.1. So because of this, we can now state our problem more completely. We have an initial value problem. There's the differential equation with the initial value telling us the amount of material, in this case at time 0. So as we saw in an earlier video, to solve the separable equation, we first separate the variables. So in this next display, we've taken all the A's to one side and all the T's to the other. I've done this by dividing both sides by A and multiplying both sides by dt. Once variables are separated, we integrate. So we have the integral of 1 over a dA is the integral of k dt. So to perform this integration, remembering k is a constant, these two integrals are really pretty easy. The antiderivative of 1 over a is log of the absolute value of a, as we saw when we studied logarithms. And because k is a constant, like a 2 or a 3, its antiderivative is kt. And we've added the constant integration on the right. Again, remember there really is a constant integration on both sides. We bring them together to combine. Now we can isolate the A by exponentiating both sides. So we come over to the equation, we just take e to the power of each side of the equation like that. That gives us the expression down here. We have e to the absolute value of e to the log of absolute value of A is e to the kt plus c. And then we've used rules of logarithm kind of backwards down here to pull this expression apart into the one on the right. Now here, if we had gone from this point over to here, we would simplify this expression by adding the exponents to get the one over here. Those identities work both ways, so we can also break this apart and write it as e to the kt times e to the c. The reason we do that is that, of course, the c is a constant, so e to the c is just a constant. And we're going to call that c1. And so down here, we've just replaced the e to the c by c1, a little easier to look at, a little easier to write. Because the exponential and logarithm are inverse functions, we can write the e to the log absolute value of a as absolute value of a. What happens here. And next, because we know that a is non-negative, it is an amount of material, so it cannot be negative, we remove the absolute value signs in the next step to leave us with a equals e to the c1 kt. This is our basic expression to describe exponential growth, or in this case, decay. Now we went through a bit of a process to come up with this, doing this separation and integration. In the future, when we see an equation like this, dA dt equals Ka, we will just jump right to this expression. So we've solved this equation once, it'll show up a lot. So when you see something of this sort, you're free to go ahead and write down the solution in this form. A equals a constant times e to the kt. Probably further work will be needed to determine the values of the constant c1 and the value of the constant a. We're going to go ahead and do that right now. So proceeding, the initial condition, a of 0 equals 0.1, because we started with 1/10 of a gram of iodine 131. This can be used to determine C1. So all we're going to do is set t equals 0 in the equation up here. When t equals 0, we have a of 0, which we know is 0.1. That's what we're told. We can also plug 0 into the exponential part there, the other expression for a, and get e to the power k times 0 times c1. E to the 0 is 1, so that just results in c1. And so our c1 is 0.01. We'll put that in just a moment. we can use the half-life to determine the value of A. So we know that the half-life is 8.07 days. That means if you have an amount of iodine 131, say amount B at some time, and you wait 8.07 days, by that time you'll have B over 2 left. So half-life means during any 8.07 days, the amount from when you start to the end of that period, the amount drops by a half. So here we have A of 0 equals 0.01 because we start with 0.01. So that means that on day 8.07, we should have 1/2 the amount, or 0.05 grams. So here's an expression that relates A to an input to an output value for A. So 0.05 is A of 8.07. And again, if we make use of this expression for A down here, with our C1 value now of 0.01, we have 0.05 is 0.01 e to the k times 8.07. We can solve this for k with the help of logarithms. So to solve for k, we're going to first divide both sides by 0.1 and then take logarithms of both sides. So the division by 0.1 is here, and of course that expression is just 1/2 now. And then in the next line we've taken the logarithms of both sides. So the log of 1/2 is the log of 8.07 times k. And again, we use the fact that the logarithm and exponential are inverse functions. So this simplifies to 0.807 k. So as is often the case, we use logarithms to get at an unknown up in an exponent like we had here. Okay. So we just divide by 8.07 and we have k, and that's what happens in the next step. So k is the log of 1/2 divided by 8.07. Nothing wrong with this expression, but log of 1/2 is a little awkward. If I use rules of logarithms, I can write the log of 1 over 2 as log of 1 minus log of 2. And because log of 1 is 0, this becomes minus log of 2 over 8.07. And calculator says that's minus 0.0859 approximately. So we can now update what we know about A of t. We now know A of t is 0.01, that's the C1 value, times e to the k, which is minus 0.0859 t. So here's a formula for A of t. It gives us the amount of iodine present at any time t after our initial production of that 1/10 of a gram. We can finally answer the question in the problem, how much I-131 is left after 2 days. So we're asking for A of 2, and so all we need to do is plug 2 into our expression for A up here. And so A of 2 is going to be given by 0.1 e to the minus 0.859 times 2, which with calculator works out to be about 0.08242 grams. We start at 1/10 of a gram, that is 0.01, and after 2 days, we've lost about 0.015 grams, so a little bit. And of course, the decay keeps going on. By the time you hit day 8.07, we're down to 1/2 the initial amount, or 0.05 grams. So practice some of these. Very likely something of this sort will show up on a final exam. Make sure you understand the definition of half-life, what it means. If you work in a situation where you're looking at exponential growth, like the growth of money or the growth of population, you might hear the expression doubling time. How long does it take a population to double? How long does it take your money to double? So with exponential growth, doubling time is often important. With exponential decay, half-life, or the time to lose 1/2 of what you started with, is also important. So practice some of these and have fun with them.